let's go for it. He's very well known for his work on Gaussian processes, and in particular, latent variable model Gaussian processes and deep Gaussian processes and all these other cool things. And going through his bio, I was trying to find sort of interesting factoids to share with you. But I'll have some for you later. But first, let's go through the more boring stuff. He did a PhD. It's boring but impressive, I would say. He did his PhD at the University of Cambridge. He then went on to work for Microsoft Research. He became a lecturer at the University of Sheffield, then moved on to the University of Manchester, only to return to the University of Manchester again as a sort of collaborative chair in neuroscience and computer science 3 years later. But what did Neil do before he did his PhD? Any guesses? He worked on an oil rig. So that's a very interesting factoid. I want to talk to you about that after the tutorial, how that is. But more seriously, Neil actually has served our community tremendously. I'm going to list for you basically all the things that he did for the machine learning community, and that's a truly impressive list, I think. So he was an associate editor-in-chief for TPAMI, which is basically one of the highest-ranked journals in machine learning and computer vision. He was a founding editor for the Proceedings of Machine Learning Research. He was both general chair and program chair for AI Stats, and he was both program chair and general chair for NIPS. He was also one of the founders of the European version of NIPS, which is DALI, and he also founded Data Science in Africa, which is also a very interesting initiative where people teach machine learning in Africa. So you see, Neil is all over the place, and he's really shaped our field tremendously. And more recently, he had a new adventure and joined the corporate world, and he joined Amazon. He founded something yet again, in this case, the Amazon Research Center in Cambridge, where he will be, or he already is, the director of machine learning. So very, very impressive resume. And we are looking forward to your tutorial on deep probabilistic modeling with Gaussian processes. A big hand for Neil.
Thanks very much, Max. I don't know what that sounds like over there, so people can... I don't know what you can do. You can shout, but I won't hear you. Just trying to remember my password in front of 1,000 people. Okay, so it's a real pleasure to talk at this meeting about deep Gaussian processes because it puts me back in mind to my first NIPS. And the first thing I saw, it was 20 years ago, in 1997, was a tutorial on Gaussian processes by David Mackay. David Mackay was a big influence on me and many others here. And what I'm going to try and do in the tutorial today, it's very hard to talk about all the things that have happened in the 20 years since then. And when I look out at the audience, I see some people who are like totally expert in this stuff and some people who probably just saw deep in the title and thought they'd come. So a mixed audience, I would say. So I'll see how well I do. Okay, so I thought I might start with what my perspective on machine learning is. So I think of data and models leading to predictions as being what drives us in machine learning. Gaussian processes are about the models. So the data are the observations we actively or passively acquire, and the models are assumptions based on previous experience, other data, transfer learning, beliefs about the regularities of the universe, or inductive bias. And I want to make these predictions with as rich a family of modeling as possible, and actually deep neural networks are a very rich family. And I was very inspired by early work by Jeff Hinton on deep Boltzmann machines to look at the deep methodology in the context of Gaussian processes. Now, what's interesting to me now is that I definitely never was doing AI, but apparently now I am doing AI. I've always been someone who was doing machine learning, but that's because machine learning has become the sort of mainstay of AI, and that's because of the importance of prediction. Now, the thing I'm going to be arguing today is that that's not enough to do AI. You need to make decisions on top of predictions. So it's one thing to be making a lot of predictions about the state of the world, but you actually have to decide how to act. Now, some areas in machine learning do that, like reinforcement learning. But my argument or my belief has always been, ever since the early years of machine learning, that in order to do that well, you need to use uncertainty. Now, to combine data and the model together, I always think that there's two functions you need. So the prediction function, which is the thing you're going to use, there's this new word, inferencing, which I'm not sure where it came from. It used to be called prediction. When I say inference, I'll be using it in the classical sense, not meaning prediction. So the prediction function, which we use to make sort of predictions at test time very often, and that often includes those beliefs about our regularities of the universe, and the objective function, which defines the cost of misprediction. Now, I think there's a misunderstanding with a lot of probability is that basically the cost of misprediction, you actually defer that. So the idea in the probabilistic approach is you simply do your modeling. So your objective function actually becomes to fit your probabilistic model to data. But the objective function in the real world also normally encodes other things like costs and so on and so forth. Now, I mentioned uncertainty, so I wanted to be clear that uncertainty comes in all sorts of ways. So the main uncertainty we're going to be looking at today is that arising from scarcity of the training data. So even if you have the right set of prediction functions, if you don't have enough data to determine your parameters, that leads to uncertainty. There's also your model choice, so the mismatch between the set of prediction functions we choose to use for practical reasons and all possible prediction functions. That's a major interesting source of uncertainty, and one that when we're trying to understand the quality of decision making, we need to account for. Now, I think my favorite type of uncertainty is one that you rarely hear talked about, which is actually the uncertainty in the objective or cost. I mean, I don't even know what I'm doing. Why should I know what anyone else is doing? So I think the main thing you see in real intelligent systems is massive uncertainty in objectives. And that's, I think, something that we're very limited in machine learning. We write down objectives and then we riff off those. But I'm not going to talk about that at all today. So I'm actually going to be focused mainly on this idea that I've chosen a class of models and I'm going to have uncertainty in the training data. So I was sort of thinking, it's 20 years since David presented a tutorial on Gaussian processes. And that makes me think also about the history. And if you have to go all the way back to McCulloch and Pitts, I actually got out the paper. It's not very clear, their model of the neuron. But that underlies a lot of the work that we are doing, or people are doing in the machine learning community at the moment. Of course, there's an association with those models, but actually the really interesting thing about these composite deep neural networks is their ability to sort of express what we think about the world, to use highly complex functions. So that's the same motivation for why you're interested in deep Gaussian processes. But what I'm going to have to do in order to introduce that to those who aren't familiar is introduce the idea of, or sort of review the idea of a one-layer neural network. Because that's going to make it easier to build up deep Gaussian processes from that. So I said prediction function, objective function, and I'm not going to talk about objective functions at all today. I think, as I say, they're critical. And in fact, how you define your objective function can lead you to all sorts of different directions. But all I'm just going to focus on is the quality of that prediction function, the thing that encodes the nature of the regularities of the universe. Now, I'm going to use this notation. It's a little bit ugly. F of x is my prediction function here. And then I'm saying, for a neural network, I'm just going to use this phi, which comes from statistics. So it's a basis function notation. But think of that as the activation function. So the one-layer neural network, and of course, I've not put any output nonlinearity, so this is like a regression neural network, is equal to the inner product of some vector of weights, which is one output in this case, times a set of basis functions. Now, those basis functions themselves are a function of the inputs and a matrix W. So if this was like a classical multi-layer perceptron neural network, this function here would be W times x. That's W is a matrix of weights from inputs to the hidden layers. X is the number of inputs. And phi would be just take the hyperbolic tangent from that vector. So W times X would be a vector. That would go into the hyperbolic tangent, and then this says weighted linear sum of that output. So I'm just laboring this because this is the notation I'll use because it makes it easier to turn it into the Gaussian process setup. So that's very simple neural network. It's the sort of thing that in 1997 I sort of got interested in the field, in 1996 even. And this is what people tended to be working on. They worked on convnets as well, but there was a lot of work on this. Now, I like this setup because it shows this important relation with statistics. In statistics, as I said, activation functions would be known as basis functions, and we would think of this as a linear model. Now, that terminology is important. I don't mean it's linear in the predictions, it's linear in the parameters. So in statistics, when they say linear model, they're referring to the fact that these parameters here, W, it's not linear in these parameters, W1, but W2, I've got lots of W's, sorry. But it's nonlinear in the inputs, right? So when people in machine learning, they typically say it's a nonlinear model, they mean nonlinear in the inputs, but the statisticians noticed this nice thing that you could have something that's nonlinear in the inputs, and then you just concentrate on these parameters. But that's an important difference. So in statistics, they typically would choose this set of parameters by some other means. You wouldn't look to fit them simultaneously. So the sort of interesting phenomena in the neural networks, certainly already there in the first wave of neural networks, was that these are adaptive basis functions. Basis functions where you attempt to fit this matrix of input to hidden weights alongside the sort of hidden to output there of weights. So they would call that a linear model, and in that case, W1 would be static parameters. There's lots of advantages. So when you watch how a statistician works, if you're a classical machine learner, you'll see they work in many different ways. That's mainly because they're driven by different objectives, and interpretability is key among them. That's going to come back to us, actually, because the interpretability of our models is also going to prove important. They focus on interpretability more than prediction. So they tend to look at model classes and treat them in such a way so as to keep things interpretable. So they might be happy sacrificing W, making them static, to give them worse prediction performance, because by staying in this class of linear models, they get better interpretability on what's going on. And by the way, this class of models is also what Gauss fitted, why the Gaussian is named after him, when he was trying to plot the orbit of Ceres and predict where it was going to reappear when he was 23 years old. Only in his case, the basis functions were derived from understanding of the way the planets and the move around the sun together, and they were sort of derived that way. And he had to fit the parameters inside here as well. That's an incredible achievement. It took him 6 weeks. It's like training some deep neural networks today. Okay. So in machine learning, we optimize W1, this sort of, it could be a vector or a matrix of output weights as well as W2. Now, in statistics, you would normally denote W1 by beta, and I like that separation. If I ever use beta, it normally means I care about the value of those parameters for some reason other than the predictive quality of the model. If I denote them as W, it means I don't care what they are. They're just a mechanism for trying to get predictions out. So this tutorial is sort of revisiting that decision to optimize W1 and W2 and follow the sort of path of Radford Neal and David Mackay, who I mentioned was my inspiration. So David wrote his PhD on Bayesian neural networks, and that was something I also looked at during my PhD thesis. And Radford Neal also did his PhD thesis on that. And those theses are both still classic today. But we're going to go beyond Bayesian neural networks as well. But I'm going to start by looking at the probabilistic approach in that. So classically, I introduced machine learning as making predictions from a prediction function and using an objective function to try and fit that prediction function. The objective function is there to tell me the mismatch between the training data and my predictions, and then I hopefully design it in such a way such I generalize well. But something I don't think we talk enough about is that actually if you're going to predict probabilistically, in some sense, it's an entirely different ballgame. So probabilistically, what you want to do is you kind of want to have a joint model of the entire universe, right? So you actually want to have a joint probability distribution that tells you how every variable that you've observed and every variable you could observe in the future is related to each other. And then you want to make a prediction by taking one of those things that I want to make a prediction over, y star, and conditioning on everything I've observed. So that's y here. So if I observe y things in my life, if I'm going to make a prediction, and I've got uncertainty over that, somehow I'm modeling this joint distribution. And then, of course, I'd have the x of the, so y and x here are the training data, and x star would be a test location if it's a regression problem. If it's not a regression problem, it's just p of y star given y. That's unsupervised learning. So you're trying to model the joint distribution of everything you're going to see in the future and everything you've seen in the past. That's really what I want to do. I mean, so in practice, the way we actually do this in this parametric world that I've spoken about is we compute posterior distributions. So this is the classic Bayes rule for prediction. So what we have is we typically relate our test data outputs to our test data inputs by some set of parameters W. So here I've conflated W1 and W2 into the same matrix. And we combine that with what we call the posterior distribution of all those parameters, given what we've seen before. And we use Bayes' rule to compute that. So that's a classic thing that people are trying to do with Bayesian neural networks. And we integrate over these parameters. But the parameters, I think one thing you shouldn't forget, we don't care, we're machine learners, we don't care about the value of those parameters for anything other than they're a sort of intermediate step for making a prediction. So that's something not to forget, right? So we're integrating them out, and then we have this object here, which is what we make predictions over. Now, in practice, this is hard because of a lot of the integrals required to get these probability distributions out are difficult to work with. So in practice, we might do things like make map approximations here or other approximations to try and get things to speed up. It's a very elegant framework, but difficult to apply in practice. Okay, and of course, when we're building that, that's constructed based on the likelihood. This term here is the likelihood of the test data, but the likelihood of the test data is typically the same as the likelihood of the training data. So the likelihood P of y given x comma w is what we tend to work with. And typically, and now I'm going to mention independence for the first time, we assume independence. But be very, very careful with the independence assumption. It would be stupid to assume your test data was independent of your training data. If it is, you've got the wrong training data. Your test data is correlated with your training data. So when you're making an IID assumption, you're not making an IID assumption about the, and people sloppily say this all the time, about the data points between each other. You're making an IID assumption conditioned on the inputs and W the parameters. So actually what you're doing is you're making an IID assumption about the noise, not about the actual underlying function. And the different thing when you start looking at Gaussian processes is you sort of throw that away. Or if you look at the general probabilistic approach, you throw that away. So when people think they're being probabilistic, very often they're just being probabilistic about the noise. And that's a fine thing to do, but it's a very small fraction of all the framework of probabilistic modeling you could do. And in fact, it was proposed by Laplace to do this, and it was the approach Gauss used. He had the probabilistic justification for his model when he predicted series. Very commonly, we might have a Gaussian likelihood, and we like Gaussian likelihoods. The reason Gauss didn't actually invent the Gaussian distribution, Laplace invented it. Laplace invented it for doing Bayesian inference. That's why it's called the Laplace approximation when you do Bayesian inference with this. So this form of distribution, Gauss noticed that when you maximize the log likelihood, you got a quadratic, and that was easy to solve, and that's what the likelihood he used for series. So that's classically what we use, and people often think of doing model fits. It's interchangeable between a least squares objective and a Gaussian likelihood. We can also consider, though, priors over latent variables. So the other thing that's very core to what I do is to take regression models, those prediction functions, and turn them into unsupervised learning models. And the approach to the way I do that is to integrate over distributions on the inputs. And of course, this is what a GAN is doing as well. Although it's not fitting the likelihood, which is a very interesting thing. And, other types of models. You're viewing these as nuisance parameters. So this is my framework for trying to construct a general model, that I want P of y star given y. So I might not even have regression inputs, but the way I build it is I try and build from a likelihood, which I typically assume to be independent. There's an implied posterior in there, and then I integrate over P of x. But this is, for me, what it's all about. All that stuff looks very, very complicated relative to what we're actually trying to do. Machine learning, for me, is very simple. You have data y, you have a model, y comma y star, joint distribution of, and you do conditioning in order to make the prediction. But actually, very few people even think about this when they're doing machine learning, and the main reason is because in order to get from this joint distribution to this prediction here, you have to do high-dimensional integrals. So in this case, this is a shortcut by going through W, right? So we built the model in such a way that we can have this sort of decomposition. But in this case here, you would just have to integrate over all future things that are going to happen in the world, integrate them out, and then you would divide that, that would give you P of y, divide that into the joint, and that gives you your predictions. But of course, that's a pretty hefty integral, right? You've got to now integrate over everything that you could possibly see in the world in the future, which is, sounds tough. Okay. Of course, there are other frameworks that have looked at this, and it's nice to see last year's NIPS, a number of those coming up, so people combining graphical model frameworks with deep learning frameworks. And I'm going to sort of, I also sort of believe in this a lot. So I guess the work that I'm talking about now does go back to NIPS, one of the Vancouver ones, so I don't remember really which year, probably about 10 years ago, where Kevin Murphy, who was working a lot on graphical models, wrote a nice book on it, and I were talking about these two different ways of trying to build joint distributions. And I was sort of saying, I like doing it this way, where this for me was a regression model, and then this is a latent variable, so I took a dimensionality reduction. And that seemed to be a nice way of trying to specify a large joint distribution with a reduced number of parameters. Whereas Kevin was very active working on probabilistic graphical model inference. Now what that is its assumption about the way this joint distribution decomposes, where it factorizes. So this chain here is a Markov chain, and it's saying it factorizes in that way. And I started out by having a little discussion with Kevin about, he probably doesn't remember this, about how surely this was the wrong way and what I was doing was the right way. But then I sort of concluded, like as many of these things, that a combination of the two of them was the right thing. Now that combination of two of them, to my mind, is what people are doing when they're doing deep learning. And I think also to the early researchers in that field, they also saw it very similarly. Because this is the challenge with a graphical model. So I just searched, I think earlier this morning, for a paper. The promise of graphical models is, with these sort of decompositions, we could put joint distributions over everything we cared about, and we can make predictions about other things we cared about. But in order to do so, you end up with quite complex graphs. So this is actually quite a small graphical model. It still wouldn't fit very well on the screen. You can't read it. And the title of this paper is Predict Perioperatic Risk of Clostridium difficile Infection Following Colon Surgery. So this graphical model is for predicting one thing about a patient after a particular surgery, right? It's quite a lot of effort. It's not really going to give you this thing that you want of being able to predict all future things given the past. And one of the reasons is, I think, because the relationships between these different nodes in the graph are relatively simple when you're just using conditional probability tables. So you can't capture the richness of what's really going in. You can't abstract things. I think that the key thing about deep learning for me is its ability to try and abstract things. And so in some sense, this was always forlorn, because actually you lose interpretability as the graph size increases. But combining these things with other models that do powerful function prediction would seem to be quite promising. So I think I've said these things already. It's easy to write everything in probabilities, but underlying that, so you can write these things down in terms of probabilities. You can make any distribution up you want, but then you find you can't normalize it because you can't do the high-dimensional integral. The worst high-dimensional integral being, I now have to integrate over all future data that I've never seen before. Oh, somehow I've lost the, damn it. Compile talk. That's a, Okay, so just trying to work out what that equation was that you can't make out. Anyone who can read LaTeX can tell me. So statistics has focused more on that linear model. So that equation, what is, I believe, just simply going back. There was an error in it, and by fixing the error, I've now made it unreadable. Come on. Way back. This is why you needed the reminder. It's that sort of neural network equation. Oh, God. Gee, I've done a lot of the talk already. Okay, now it's doing it on its own. That's great. Okay, I might intervene now. Knowing when to intervene is critical. Okay, let's see if I do that. Okay, let's... Wow. I think the internet's slow. I think that's causing me problems. Okay. Okay, that's going a little bit better now. Okay, back to that equation. It's that one. I've got to go forward again. Okay. There is a good way of doing this on this thing, but I'm not really that familiar with it. Okay. Okay, it wasn't that far away. There was something weird there, wasn't there? Okay. Predict over everything. Uncertainty is critical in all decision making. So that equation, I didn't give you any chance to look at it. It's the W transpose phi of Wx. And then in statistics, you might focus on this linear model. And then if you want to do a probabilistic treatment, it's actually quite nice. It's quite easy to do because you can place a Gaussian prior over these output weights, the W's, that they would call beta. And now you define yi is equal to f of x, where f of x is defined by that missing equation. F of x is equal to W2 transpose phi of W1 comma x, the single layer neural network equation. And then this is how you define your probabilistic model. This is what Gauss did, actually, and Laplace before him. Laplace was the originator of this type of idea. You say that you've got some function, which is a parametric function in this way, and it's being corrupted by noise epsilon I, and then you define that the noise is sampled from a Gaussian distribution. That's the IID bit, right? Okay. So normally the integrals are complex, but for this Gaussian linear case, they're trivial, and that's kind of why Gaussian processes are very special. They have this very unusual property that I'll just go through now. So Gaussian distributions do. So univariate Gaussians have this property, which is that if a y, it's not a test y, it's a general y now in this case, or a training y, it's just a general y, is sampled from a Gaussian distribution, then adding those y's together, the result of that will be drawn from a Gaussian where the mean is the sum of the means and the variance is the sum of the variances. That's a really, really nice property. It's also unusual. In fact, when you do it to most other distributions, they start becoming Gaussian, right? Because of central limit theorem. You're adding random variables together. So it's unusual to find this property. Poissons do it, and gammas with certain parameters do it. Is that right? I'm not sure about the gammas. Let me reverse. Can't think on my feet. Poissons do it. But when Poissons do it, they sort of start looking like Gaussians as well. So also scaling a Gaussian leads to a Gaussian, so that's not that unusual. So scaling a Gaussian, scaling lots of distributions keeps you in the same class. So this is the sort of relationship there. But the important part about that is that when you do linear algebra on Gaussian random variables, linear algebra is just scaling and summing together. So everything stays Gaussian. And that's super, super important. That's why Gaussian processes and Gaussian variables are so critical, because computers do linear algebra really well. Matrix vector multiplication, or what is it? Computing a neuron in the other parlance. That's what GPUs are good at, right? So now we have, if that's the case, we've got this multivariate consequence that if x is drawn according to this distribution, And if we say y is equal to a linear algebraic form, w times x, so y is a vector, w is a matrix, x is a vector, then y, the vector y, is drawn from a multivariate Gaussian of this form, which is just a modified variant of this. That is normally considered to be a very difficult integral, because that, effectively, this is defining p of x, this is defining p of y given x, and this is p of y. So multiplying these two distributions together gives you the joint, and integrating out gives you the marginal. That's the difficult thing. But in a Gaussian process, or in a Gaussian setup, it's trivial. It's just linear algebra, which is amazing. That's why we like them. So these linear Gaussian models are much easier to deal with. But the really interesting thing, and this was the sort of insight from Radford Neal, is if you go to these models, you can deal with that W2, the output weights, but we're also going to look briefly at the fact that you can deal with the input weights, the weights inside the basis function under certain conditions by considering a particular limit. And that's how it gets us to a Gaussian process. So I'll skip that one. So just to sort of give you a little, I'm going to move to some matrix notation. So I just want to introduce that matrix notation. So before, the activation functions were of this form, but there was a vector of them, right? So it was W transpose phi vector, because that's all the hidden units. This is like the result of one hidden unit for a particular data point, I. So the ith data point, it's the output of one hidden unit, the jth hidden unit, because the vector's j, for the ith data point. And what we typically do in statistics, and also I try and copy their approach in machine learning, is take these values which form for a given training set a matrix of values. So this matrix is the first hidden unit, the first data point, the first hidden unit, the second data point, so on up to the first data point, the first hidden unit, first data point, second hidden unit, first data point, h hidden units, so h in total. And then we've got a number of rows going down here, one for each data point. Now, the advantage of that nice form is that we can re-represent that output of the neural network, or the basis function model, whatever we ever call it, in this matrix form. So, sorry, that shouldn't be f of x there, because I've corrupted by noise. That should be y, little error there. It's funny how you only spot the errors when you actually give the talk. Vector y is equal to the full design matrix, which is n rows and h columns. W is the hidden to output, so that's h rows and one column, and then this is a vector of noise that's going to corrupt it. So the result of this is n by 1. So this is a way of writing down in matrix form what the output of that neural network looks like. So we pre-compute the basis functions, and then we just do linear algebra. Now the nice thing about that is, if we now define a probability distribution over this parameter set w's, we can use those rules of multivariate Gaussians to immediately see that y is jointly distributed by a zero mean Gaussian with this covariance. Okay, so let's go back through that a little bit slowly, because it's cool, I think. So this is what we're saying y is, and we're saying y is matrix phi times vector w plus epsilon. Epsilon is noise. Going back to here, not this one, let's go to this one. If y is w times x, then this is the consequence, that y is distributed as w times the mean. The mean in this case was 0, and the covariance was, in our case, later on, it's phi times w. There's a little bit confusing there, isn't it? So capital phi times w vector. So that comes out here as phi times the covariance of the prior over w times phi transpose, and that's what we'll see in the result. So, looking at this object here, it's phi times phi transpose. That's coming from the first term, that y is equal to capital phi times small vector w, and then there's an alpha popping out the front, because that's a scalar. Now, because we corrupted by noise, we added Gaussian noise to this Gaussian thing, there's also a plus sigma squared. Now, the really interesting thing about this object is it's no longer IID, right? So people are used, this is for the training data. So people are used to describing their training data as IID. So they have independence over y. This object is a zero mean multivariate Gaussian, the covariance of which is n by n, right? So it's the size of the data set. So what this object says is all your training data are correlated to each other in a Gaussian way. And we tend to call that object the kernel matrix, the kernel function. So this one that I've derived here is of this form. That's the one for, say, a neural network. So a neural network is already a Gaussian process where you've integrated out the front weights. But it's a particular type of Gaussian process. In fact, it's a degenerate one. So, but rather than writing down these basis functions, what we tend to do in the Gaussian process world, and also kernel methods have the exactly same object with a totally different motivation. By the way, be careful with that. There's a challenge that there's only a certain amount of maths that works, right? Most maths doesn't work. You can't do most integrals and so on and so forth. So there's this very misleading phenomena that people use the same set of maths with a different goal, right? And then people argue about whether they're using the maths right. So the way I imagine that is we're crossing this massive desert of a landscape where we can't go anywhere. We're all trying to travel in different directions on the other side. But when we go along the way, we often use the same set of maths. So the motivation as to why they use this kernel function in SVMs is very different. It's all about Hilbert spaces and complex maths in Hilbert spaces. But the same object comes up in Gaussian processes, and you can do a lot of the same analysis. But the initial motivation, utterly different. And motivation is important in terms of what steps you make as you're designing your algorithm. So I said we represent in the covariance function, and this is the form of the covariance function in this case. This is now the vector of all hidden unit outputs for the ith data point in a product with the vector of all hidden unit outputs for the jth data point. And that's the correlation for your function. Now, it's also got a noise term added. I'm just looking at this part of it here. That's the correlation for your function. So it's this inner product, this sum here. Okay, so that's the Gaussian process basically primarily introduced. I'm going to give you some intuitions about it in a minute. So instead of making assumptions about our data as being IID, we do have a function assumption in there, actually. We've got a function assumption. We said it was a neural network, but it's led to this object that is a multivariate density over all data points. The covariance matrix is a function of both the parameters of the activation function W1, so the inputs to the input to hidden layer, and the input variables X, so all the input variables X. The covariance matrix is a function of both of those. Now, W1 can be quite large. If we have very high-dimensional inputs and we've got a large number of hidden units, as we might like, that could be a very big matrix. So we've integrated out, actually, the very few parameters relative to the number of parameters we might have on our input. Okay. Now, those basis functions themselves can be very, very complex. And you'll see a lot of work now on people doing various things. You can make that basis function a deep neural network, a convolutional neural network. You can have it as some output from a recurrent neural network. You can do all sorts of things. But you can also look at neural networks in this way, and actually the often Sajedi paper on batch normalization, you can sort of see the analysis they're doing is very similar, because it's about the output of activation functions and normalizing them to stay in the range where you've got gradients, right? So the math they're using is Gaussian process maths to try and sort of, well, I would view it that way, other people might view it slightly differently. We're all traveling on the same road, in order to come up with the conclusions for that, right? So it's very useful to understand this perspective on these things, even if you're doing neural networks. But something about that process is that it's degenerate. So what do I mean by degenerate? Well, this covariance matrix is at rank of at most h. So what do I mean by that? Because if we look at the way the covariance matrix is formed here, this is an n by h matrix by an h by n. So that's the bit that's looking after f. This is the corruption that gives us y. If we look at the rank of this part here, its rank is at most h. So that means that you've got problems when you try and use it within a covariance, in a Gaussian density, because the Gaussian density has in the normalization the determinant of the covariance. So if you drop the noise term, if the noise goes to 0, then k has a determinant of 0, which means it's not a valid Gaussian distribution. So when n goes to infinity, that's what happens. The covariance matrix isn't full rank. And that's indicative of a problem, right? It's indicative of the same thing that happens if you start with a neural network. Let's say, I don't know, probably a lot of you have to train neural networks for a living, and someone knocks on your door and says, I need a neural network I've got 1,000 data points. Okay, and you go away, you build your network, I don't know, do something with the data. I don't know, and you have a one-layer neural network, so you have 100 hidden nodes. Okay, but then, it's an industry environment, so next week they come back later and they say, oh, actually, I made a mistake, I've got 1 billion data points. Are you going to use the same neural network that you trained on 1,000? Probably not. And the same thing's sort of going here, actually. So the number of hidden nodes, you're probably going to increase them. But what happens if that's what's going on in real life? If in real life your neural network keeps retraining and keeps having to learn new stuff, right, sees 1 billion things, you don't know how long it's going to be in production. You've actually a priori designed the capacity of your neural network, and that's coming through here in this degenerate Gaussian process. That's what we call the degenerate Gaussian process. It's like considered a bad thing, because it means that the model can't respond to the data as it comes in. The model's parametric. It's not what we would call non-parametric. So, Radford Neal, he was doing his PhD thesis on Bayesian neural networks. If you are working on Bayesian neural networks and you haven't read Radford's PhD thesis, you should stop working on Bayesian neural networks and go and read Radford's PhD thesis first. It's still an amazing read, as is David's. But Radford's thesis, he actually looked at Bayesian neural networks and he said, well, what happens in the case where I decide to have a Bayesian neural network with infinite hidden units? So he said people want larger and larger number of hidden units, and this is page 37 in his thesis. And this is where he decides to take the limit as the number of hidden units goes to infinity. Now, as he does that, he has to scale down the outputs weights on those units to make sure the function doesn't go to infinity. And roughly speaking, this is the sort of idea that the kernel function we've just described is of this form: alpha inner product between hidden units associated with input I and hidden units associated with input j. So that's a sum, right? I like to use the linear algebra, but just for clarity, that's a sum over all the different basis functions. Now, the classic way you go from a sum to take the limit to infinity is you replace that with an integral. And so the analysis that Radford did says, well, what I'm going to do is I'm going to have infinite hidden units, and I'm going to treat them by every hidden unit has its set of parameters, doesn't it? So every time I get a hidden unit, I sample the parameters from a probability distribution that I've written here, P of W1. And then I keep doing that for every single hidden unit. And then, so rather than getting a fixed set of parameters here. And if you do that, then you get this integral instead, or roughly speaking, you get this integral. I mean, you can read Radford to see the nice results. But because of the central limit theorem, so it turns out P of W doesn't even need to be Gaussian. The prior over the input variables doesn't need to be Gaussian. What you do have to be careful of is you have to scale down, as you increase the number of units to infinity, as I said, you have to scale the output variance of the whole thing by h, otherwise the output of the function blows up to infinity. So just to give you a sense of what you're doing here, there's a little probabilistic program, not a very complex one. What you're saying is I'm sampling, every time I get a new activation unit, I sample the parameters for it from a probability distribution. And then the activation associated with that unit, if I call that phi I, that's now a random variable, right? If you think about that, if I'm sampling random variables on the input, phi I is a random variable. If that has finite variance, what's going to happen next? Well, I'm just going to sum up all these phi's weighted by the w's, right, which are also sampled from a probability distribution. As I take that to infinity, central limit theorem applies as long as the scaled output of these things has finite variance, yeah? So as long as the scaled output of these hidden units is finite, I can take this limit and I get a Gaussian process. Nice. So sort of further reading on that, I think chapter 2's read of Neal's thesis is excellent. The rest of Neal's thesis is excellent. All of David Mackay's thesis. I mean, they're very informative about these things. But the result is this sort of amazing thing, which is this object where you can... So this, what I'm going to show you now, is kind of all Bayesian inference. The objective in Bayesian inference is you have this model, and it gives you ways of expressing, like you can sample from this model about what you think the world looks like. So I've taken like 1,000 samples from a Gaussian process. I'll give you a bit of intuition on how I do that now, in a moment. But then when I combine them with data, I've got 3 data points here. I throw away all those functions that don't go through the data, and I just look at the ones that remain. That's actually not Gaussian processes. That's just what you're trying to do in Bayesian inference. You've got some complex model of the world. In fact, there's a wonderful technique called ABC that does almost precisely this. Very complex model of the world. You sample from the model of the world many, many times, and you throw away samples that don't go near your data. It's extremely expensive, but sometimes it's worth doing, particularly if you're on AWS. That's actually a distribution over functions. So what does that mean? Where did these samples come from? So I've got this process where I can sample these things over all the space here, and then I'm going to throw away any data that goes through, doesn't go through those points. That means I should be able to sample these processes. So I'm going to try and give you an intuition about how we do that. So what I'm going to show you on the next slide is one single sample, but it's got 25 points in because it's from a multivariate Gaussian. So it's trying to give you this intuition about what's going on. So one sample here from a multivariate Gaussian distribution, right? So I plotted these points against their index. So it's a 25-dimensional Gaussian. So one sample, but it's got 25 points, 25-dimensional Gaussian, one sample. But this is the covariance associated with it. So the multivariate Gaussian has a covariance of this form where the cyan is correlated and the yellow is uncorrelated. So if I look at any 2 neighboring points, this is why Gaussian processes work, what I'm about to do. Effectively, to look at these 2 points, let's say that these are my 2 y's, right? Like I said before. And then there's y star, which is the things I want to predict in the rest of the world. But these are my y's. So in order to work with these 2 points, I have to integrate out all the y3 up to y25. That's typically hard. That's typically very, very hard. In a Gaussian density like this, all you need to do is look at the covariance. This is a 0 mean. I should emphasize that as well. I've sampled this from a 0 mean. So it looks like there's a curve here, but the mean is 0. So all I have to care about is the covariance. And all I have to do is focus in on the upper 2 elements of the covariance. That's the covariance that I need to give me the joint distribution of y1 and y2. It's beautiful. And since it's gone cyan there, now I'm showing you the values. So what it says is that those 2 points are strongly correlated. If we look at correlation coefficient, it would be 0.98 with each other. So y1 and y2 are very strongly correlated with each other under this covariance. Doesn't matter what the other data are doing, this is the distribution for those 2. And I can even plot it in a 2-dimensional contour. So this contour is showing you the joint distribution of, well, it's called F1 and F2. I'm interchanging between, when I say F, it means the noiseless process. Y is the process with noise corrupted. I've not been very clear on that. Apologies. So what I have here is this contour. This is one contour of that multivariate Gaussian. So it's very strongly correlated. And I can ask the question, you know what I said before? I said that machine learning is all about prediction. So I can now use this to ask the question, if I've observed F1, what should my prediction be of F2? Well, that's the probability of F2 given F1, which is Gaussian conditioning. And it turns out to also be Gaussian. That's also very unusual. Like most distributions won't do this for you. So what it says is, if this is my covariance that's coming from that large multivariate covariance, and if I just look at these 2 points here, and I only know F1 and I want to predict F2, it says that F2 is also Gaussian. And look, F1 was in the negative quadrant. It's saying F2 is distributed along the x-axis. F1 is on the y-axis. So I've drawn the pink line where we observed F1, and then I'm drawing the cyan line where we're observing F2. And it says that F2 is also likely to be in the negative quadrant, although there's some small probability of it being in the positive quadrant. If I look at F5 and F1, I actually see things are less well correlated. Oh, there's an error here. That should be about 0.5, the correlation is. I don't know why that's not updated. Now if I observe F1, and then I condition on that, and I look at F5, I see that there's much higher variance, right? So as I move away from the training point, the variance is increasing. That makes sense, right? Because I've got less information as I go away, typically, from that point. So the key object is this covariance function, because that's all I needed in my model plus data to get to prediction. I just need to do the covariance, combine it with data, and then I make a prediction over what I think is going on in the world with uncertainties. Notice the prediction is a distribution. It's got a mean, we can quote the mean prediction, but it's got a distribution. Very elegant. You can imagine what I felt like 20 years ago as someone who'd been interested in neural networks and graphical models, hearing David talk about this. But it actually took me about 3 or 4 years to get in the situation where I started working on Gaussian processes. So the really nice thing about this setup is that you can make the prediction of that mean. That mean becomes a function because k itself, like those, is dependent on those basis functions. So the mean is a function of the covariance matrix, and it involves this inverse of the covariance matrix here, k. That's the covariance matrix for the training data, and we can compute the covariance between future test points and the original training points, and that's our training observation. So it's dependent on all those things, just like a neural network prediction would be dependent on the basis functions. But as well as the mean, we can predict with the variance. We get a posterior covariance associated with it, which is very cool. So this object here is the posterior covariance, the posterior way that those functions move. And then rather nicely, we can actually turn it into this linear product where alpha is a sort of vector here. Okay, so going back to the thing we had before, all Bayesian inference methods can do this, throw away data that's not near the samples. That's easy. What Gaussian processes allow you to do is this. You can analytically compute what the mean of that population is and its covariance at all points. It's beautiful. Okay, so different covariance functions. I said that the object that was at the heart of this was the covariance. Different covariance functions have different effects. So what you're seeing here is the covariance function I use for that prediction. And this covariance function comes about. There's a really nice NIPS paper by Chris Williams where he derives 2 of the covariance functions I'm about to show you. This one is derived, people know, like RBF networks. If you take the infinite limit of an RBF network under certain assumptions, you get this covariance function. Where you're taking the infinite limit of the RBF network and you're distributing all those basis functions all across the space. They're not centered in a particular location. So this one here is very commonly used, and it's called like 8 things. I call it the exponentiated quadratic, just for fun. But it's also called the squared exponential, the RBF covariance, or the Gaussian covariance. I don't like calling it Gaussian because it confuses with Gaussian process. It's just coincidence that it has this form. Okay, so let's look at some data, and I like this data set here. Max mentioned Data Science Africa. The first time we taught in Africa, I was talking a bit about Gaussian processes. I used this example. This is Stephen Kiprotich, who I was teaching in Uganda, who is the Ugandan gold medalist in London 2012 for the Olympic marathon. So the data we're going to look at is the data from the Olympic marathon over the years. So marathons varied in length in the early days. So what I'm showing on the side is pace in minutes per kilometer. So the most recent winners win in about 3 minutes. So Kiprotich was running about 3 minutes a kilometer. I don't think most of the audience here could run 100 meters in 3 minutes per kilometer. It's very, very, very fast. This is an odd thing here. This was the marathon in St. Louis, where they actually got lost, and they were following cars. This is 1904, so the cars presumably weren't that healthy, and they were also kicking up dust, so they not only got lost, but they were like caked in dust and everything. My fastest marathon time is about here, a little bit slower than the speed they ran that in. So there's an outlier, which is why I like this data, and it's sort of going down over time, and we have a sense about how it should change. So this is a Gaussian process fit through it. So I've told you all these wonderful things about this. But in many respects, some of the challenges with even fitting this marvelous framework are coming apparent. Because the model is assuming constant noise, and there's an outlier, it has to put quite a large noise at, and it's placed that in all locations on the input space. It's also sort of stationary, so it can't sort of assume that the things were going on in the past have changed. It looks like there's been some transition as people worked out how to run marathons. By the way, Alan Turing runs a marathon about, he was really fast, 2 hours, 46 minutes. I can't work it out, but he wouldn't have won the 48 Olympics, but he would have been like 10th or something, which is really amazing. Very fast marathon runner. This is about 2.5 hours these people are running here. So there's some issues, right? Because these uncertainties are way too large. And it's because that covariance function, the thing when I saw this stuff for the first time, I was just shocked. I was thought, if we can do that, why the hell are we bothering with these neural networks? Because it just seemed to me, everything I wanted to do with a neural network and get uncertainty out of it and everything else was possible with a Gaussian process. Now, there's many reasons why we bother with neural networks, but the thing I didn't understand at that time is, sure, we can do nonlinear functions, but when you move into the world of nonlinear functions, then there's classes of nonlinear functions. So this one describes a class that is infinitely smooth. And it turns out infinite smoothness isn't always a good idea. I've just been given the 5, and what I was going to do is actually just show you a couple of other covariance functions, then stop for questions, and we'll have a quick break and be back here at 12. So actually this here is another covariance function that looks similar to that first one, but it's actually a fixed basis function. So there's 4 basis functions across the real line here, and you can see how it kind of doesn't look too dissimilar. These are Gaussian basis functions. This here is a Brownian covariance. So Brownian motion is a Gaussian process. People don't normally write down the covariance function. So the covariance function, so the Brownian motion is that what I move at every time step, I move in a Gaussian random walk, right? So you can see that these are non-differentiable paths, something you probably associate much more with a Gaussian non-differentiability. But a lot of the processes we use are either infinitely differentiable or multiple times differentiable. So just because it's stochastic, that's a common confusion. It doesn't mean it's not differentiable. Very interesting, that. But because Brownian's not differentiable, people often think of Gaussians as not differentiable. The form of this covariance is the minimum of the 2 times. So this is valid only in time, this process, as I've written it. So over time, what happens as you're moving forward, the variance is along this diagonal here, and the variance is just time. And of course, we know that the standard deviation of a Gaussian random walk goes up with the square root of time. So you see that directly out of the covariance here. But this is giving you the cross correlations as well. Here I've started at 0. So it's a non-stationary process as well. This one is one of my favorites because this is like a neural network covariance. So this one here, oh, and by the way, the animations of the functions are something that Philip Hennick came up with. They're like round world tours of functions. So in these very infinite dimensional spaces, you sample a function, you sample another one, and then you tour between them to give you an idea of what these functions look like, how rigid they are, and this sort of thing. This multi-layer perceptron covariance was derived again by Chris Williams in that 1996 NIPS paper, which is what happens if you take the limit of, it's not a hyperbolic tangent because that integral is not tractable, but he substitutes that with Earth functions, which look very similar. The limit of infinite Earth functions. So actually, I probably should have extended the list here. These things saturate as you leave the center because these tan H's are in the middle. So it's one layer network as well. So you sort of get quite a lot of intuition about these things. This is my favorite Gaussian process. So I'm not an expert on this at all, but Carl Kramer was talking about this at last year's NIPS. This is the cosmic microwave background. So it's the moment after, I don't know what happened in the universe, who knows? And I'm sure lots of people in the audience do, so I'll just embarrass myself by speculating. So there was some sort of plasma that light couldn't go through, and then there was some moment at which it somehow condensed because the energy is reduced enough. And at that moment, what we see is the echo of that moment, when visible light could first exist. And that's the cosmic microwave background. Because that was so hot and these particles were moving so rapidly, then it's actually, as far as I can tell, and all the physicists tell me this is true, and Kyle says this is true, a Gaussian process. It's it's in some funny coordinates because we're observing it, so I can't think well enough about all those things. But the way in which the temperatures are fluctuating has a covariance function, which is dependent on like the amount of dark matter in the universe, the amount of photons. So it's a covariance function that I think has about 5 or 6 parameters, including dark energy. So fitting the Gaussian process to that tells you what our universe is composed of, which I think is pretty cool. What we're going to look at, and Gaussian processes have lots of uses in their vanilla form, but of course the universe today isn't as Gaussian as we might like. If you lived in the universe then, you could use a Gaussian process to predict across the whole universe, all states. probably the some level at which it wasn't Gaussian, but certainly at this large level, you could have used that to predict the entire state of the universe, which is pretty cool. It's kind of fortunate that the universe isn't like that today because we wouldn't really exist. But the argument for the next part is what the universe is like is a nonlinear function. So I think that this is also sort of valid. The observable universe today is just a very, very complex nonlinear function of that underlying Gaussian process. So in the next hour, that's what we get to deep Gaussian processes. So what we're going to do is we're going to look at the case where we take this Gaussian process here, we feed it into a nonlinear function, and then we do inference over that process as well. And that's the first stage of a deep Gaussian process. So we can compose functions together, one after another, in order to arrive at the Earth, maybe. I won't do that full prediction. The data sets will be a little bit smaller, actually. Okay, so let me just see if there's any questions there. Shall I take questions now, or do you just go for a break? What do you think, Max? He said questions, please. Don't be shy. It's not a big audience. Okay, we can do questions at the end if people are a bit more reluctant.
So there's microphones. One is there. There's another microphone right there. So if you have a question, you have to walk all the way forward to ask your question.
They're desperate for coffee.
Well, let me ask a question then. So a Gaussian process also has a mean function that you can fit, but nobody fits the mean function. Why does nobody use the mean function? What's wrong? Why is everybody setting it to 0? And in the meantime, when he answers the question, and you think of your question, please move forward to the microphones.
So people do fit the mean function, but it's sort of less. They'll typically, when they have an application or they're doing something specific and they have some fundamental knowledge about how the mean will vary. Often in physical systems, you have that. Statisticians do it a lot. And they'll parameterize the mean function with like a beta times a number of basis functions. The reason why I don't like it, and there's a paper that does it with neural networks, I think it's the wrong thing to do because like you're trying to, well, it depends what your objective is like, but if you're just doing general modeling, then you've just put back in something that's not probabilistic and lost all your nice error bars. You now have to do the uncertainty on that, and that will be highly correlated with the uncertainty on the Gaussian process. So you can do it if you've got a really good reason to do it. I don't think it should be the default thing, and when you do it, it turns out to be very hard to do the sampling well, because there's a lot of, as you will know, probably you need Max to do your sampling for you because there's an enormous amount of correlation between the output of the Gaussian process and whatever the mean function you may have put in, if you treat it probabilistically. And if you don't treat it probabilistically, then that's a very valid thing to do in statistics where you care about the mean function and you're often, and they'll do this a lot in geospatial statistics, and you're actually using the Gaussian process for the noise. So that's a really common thing. That's what you'll see in spatial statistics is you might see a linear model of disease. So we might have, like, spatially we look at disease across, they come up a lot in Africa, actually, across an area. And you're trying to predict disease based on some factors like poverty and rainfall and things like that. But then there's spatial noise. And then you use the Gaussian process for spatial noise and try and put all the prediction in the mean function.
There's a question there, so please go ahead. Yeah.
Does microphone work? Oh, it does. Let's talk about kernel hyperparameters. So your covariance function, you typically like a length scale of these variances you got to put in front of these things in order to sort of fit these Gaussian processes. And the thing you'd like to do is, of course, sort of integrate out these parameters for your covariance function. But these are one of these so-called hard integrals in many cases. So a lot of people try to estimate these from maximum likelihood or something like that. Doesn't this sort of break a little bit of the elegance of the Gaussian process sort of setup? And like, I see this as sort of an unsolved challenge. Can you comment on that a little bit, on like where you see that going, and whether it can be solved or if we have to find a different framework?
So the question was about kernel hyperparameters. So what you end up with is the priors you use to put over the parameters of your basis functions also have parameters themselves, but there tend to be much fewer. So there's like 3 parameters in the covariance function I just fitted to the Olympic data. So you hope that that's better because they're fewer. If you have a lot of data, they tend to be well determined. But yes, as you get very complex covariance functions, you start doing inference over those. So you tend to look for, well, people have a range of approaches, and that's complex, yeah. But it's sort of like, I think when you look at Bayesian neural networks, people often just keep those parameters fixed. They don't even move them. So yeah, that's one problem with being Bayesian, is that, like, where do you stop? I mean, you should also integrate over all classes of models. That's the model misfit I talked about. So my own approach to that is actually, if you put a Gaussian process over the inputs to the Gaussian process, then that gives you an incredibly flexible, because a lot of your hyperparameters are encoded in that. So that's the direction I've chosen to go on. But there's lots of interesting work, and a lot of it is dependent on what your objective is.
Thank you.
Okay.
So let's take a 15 minutes break. So that means we're going to be back at 5 minutes past 12. And please be back in time. Thank you.
Okay. So at some point the universe was a Gaussian process, and it is no longer. And one reason for that is that if you start pushing nonlinearities around Gaussian processes, they become non-Gaussian. And that observation was what inspired this idea of deep Gaussian processes. Okay, so this is Kai Arulka-Romaran. So this was he put this comic together. I think he did a bit of photoshopping and something. There's probably a lot of teams like NIPS like this that are here to do this. If we want to be taken seriously by the research community, we need to come up with some theoretically driven research projects. One model to rule them all, outrageously large neural networks. I guess that's be someone like me, sparse Gaussian processes. Yeah, okay. They're not the, that was, Kai shared that on Twitter. I liked it. It's hanging, he kindly gave me a copy of it that's hanging in the wall of my office. So sparse Gaussian processes are something that we have to do in order to operate with Gaussian processes in practice. In fact, someone just asked me about this. In practice, you do low rank. So I'm not going to talk about, damn it. I've lost the slides. 1 second. See if that gives me them back. Okay, there we go. Look at that. Fixing live. That means that particular slide, unfortunately, isn't online. I'll fix that later. So this is a little example that actually one of my postdocs, James Henman, originally put together, and I'm just sort of showing it here. I don't know how clearly you can see the error bars, but there's error bars. The faint yellow is on the slide. Apologies for the color. So this is a Gaussian process fit to some data that's in two clusters with a large sort of error bar either side of it. Now, that's a full Gaussian process fit. What we do in practice to do Gaussian processes at scale, and it also is the key approximation underpinning a deep Gaussian process, is we'll very often do what we call a sparse Gaussian process. So a sparse Gaussian process is this sort of thing where we say, instead of using the full covariance function, we're going to use a low-rank approximation to it. Now, as someone just asked, does that mean we're just going back to the parametric model? My answer is a firm no, but I'm not going to go into the details of why that is now. So this is what happens if we do it to that data, right? So not a great fit. So we've chosen 6 points, which we call pseudo-observations. And what we do is we choose to compress the information in the training data into those pseudo-observations, and then we store only those pseudo-observations rather than storing the whole data. Normally, a Gaussian process is a non-parametric model, requires you to store the whole data. So if you do this naively, you get quite a bad fit like this. And so here these inducing variables are at fixed locations on the input, somewhere near where the training data was. So this would be a bit like, it's a little bit like the random Fourier features approximation. But we tend to go much sparser, and the reason is, well, if I now optimize the kernel parameters, which I can do, so we typically do maximum likelihood, and fit this model, what it will actually do is it will try and fit through with a model where the kernel parameters make up for the poor quality of the approximation. But we don't just do that. In practice, we also optimize with respect to these inducing variables. So these inducing variables, if you watch them here, if I optimize with respect to their location, they're moving out now, closer to where the data is, and that's the sort of approximation we use in practice. So we try and optimize over inducing variable locations and kernel parameters jointly, and if you compare that with the true approximation, it's not perfect, but it's not bad, given that we're reducing it to 6 data points. The hope is that for very large data, that we can approximate the process we're interested in with fewer inducing variables than there are data points, and we can gain computational efficiencies. Because the problem with a Gaussian process is the computational complexity is cubic in the number of data, because we have to do matrix inverse, and the storage is quadratic. And it's the storage that hits you first. You know, you'll get memory problems before you run out of patience. So I'm not going into the details of these approximations, but that's sort of what we use. There's a really nice review of the latest perspective on these, just published in JMLR, a unifying framework for Gaussian process pseudo-point approximations using power expectation propagation, Tang Bui, Rich Turner, and others. And then I would advise, if you're interested in how these approximations work in practice, then the PhD thesis of Andreas Damianu, Deep Gaussian Process and Variational Propagation of Uncertainty. If you really want the details of how these things are done for the Gaussian process. So the top one is for GPs in general, and this bottom one is for deep Gaussian processes. Okay. So that's the sort of really tricky maths out of the way without any maths. There's a really interesting thing about Gaussian processes is that they're mathematically beautiful and elegant, but algorithmically they're relatively hard to deal with. Neural networks, on the other hand, are mathematically not very elegant. It's difficult to say things confidently about the nature of the functions you're using when you fit a neural network, but algorithmically they're really simple. So there's this interesting dichotomy. But of course, you can use both. You don't have to go one way or the other. You can use both depending on what you're interested in doing. So this is the reason I joined the field in 1995 or something, because I like drawing neural networks. This is a neural network where we've got some inputs, and then we've got fully connected hidden layers to some fully connected hidden layer, from fully connected hidden layer to some output. I'm not looking at a sort of convnet here. I'm just looking at a multi-layer neural network. Now, what I want to look at is the maths of how that comes about. So it's similar to before, but we now have multiple layers of basis functions. So this is why I was using W all the time before, so I can keep using W. So each layer of weights is represented by W. This is the first layer after the inputs. This is the second layer, third layer. So I take the inputs, multiply them by W through the activation functions. Here I've just kept all the activation functions the same. Now, the interesting thing about this is what you'll hear. So in the Gaussian process, we talked about taking the width of the hidden layer out to infinity in an effort to improve the capacity of the model. And sure enough, in neural networks, people use very large width hidden layers, potentially thousands of units. And if you've got two sets of hidden layers, one next to each other with 1,000 units in each, then the matrix in between has about 1 million parameters. So one way of reducing parameters is, that's just the maths of each hidden layer, is to use dropout. So you actually you only train half or some portion of the hidden nodes at a given time. But what I want to sort of say here is an alternative solution, because it will lead me to a deep GP. So the alternative solution is that you can parameterize W with its signal value decomposition. So what do I mean by that? So W can be represented as a matrix U, where U is it's a K1 by Q. Q is going to be some small number. There's K1 hidden units in the left layer and K2 in the right layer, or whatever the lower and upper layer. And so U is going to be K1 times Q. Lambda is a Q by Q diagonal matrix. U is an orthonormal matrix, and as is V. And V is Q by K2. So if you multiply these out, you get a matrix of that size. Actually, what we actually do in practice is throw away that object there and just look at two matrices, U and V. So give you a pictorial representation of this. If this is the full matrix W of all the weights, what we're doing, sorry, that U is hard for me to see on the screen. What we're doing is we're decomposing it into a sort of K1 by Q size matrix, multiply it by a Q by K2 size matrix. And the multiplication of those two leads to a W, which is low rank, right? So that's another way of reducing the number of parameters, because now I have K1 times Q plus K2 times Q instead of K1 times K2. So we can draw that, and that's what I think nowadays they're called bottleneck layers. When I first introduced the deep GP in this way, I didn't know whether they existed or not, but nowadays I think that you can do this. You can put them together in TensorFlow. And it looks something like this. So I put for these linear layers, what's in effect is you've got a matrix U being multiplied by a matrix V transpose before going into H. So if we look at the math now, we've sort of given an X, we take a multiplication by V to give us Z, and then that Z goes into this basis function here, multiplies by U to give us the output at this first set of hidden layers. And we do this so on and so forth. So at each layer, here the output of the layers is being bottlenecked down to something in these new variables I've introduced called z. H is the old hidden layers we had before. So mathematically, we can write that in this form, or alternatively, we can just write this. We can say that Z1, the first of those sort of new introduced layers, is just V1 times X, but then the next of those is Z2, is V2 times the hidden layers. Now look at this object here. What that looks like is just a single layer neural network with multiple outputs. And what we can see we're doing is we're stacking these objects. So these are like vector value functions now, right? So the first bottleneck is linear, actually, in this case, but we could even drop that bottleneck if we want. And then the next bottleneck is a neural network. The next is a neural network. And then we take those Z and we just make a linear mapping. We could even drop this bottleneck if we want and just stack neural networks together, each one a single layer neural network. The point I was making before is that where we have a neural network, we can decide to take the number of hidden units to infinity, integrate over all the parameters on the input and the output layer, and then we have a Gaussian process. So that's pretty cool, because if you want to get rid of all these parameters in the neural network, you can integrate them all out and just write that instead. So you've got a series of functions where each function, x, is a function of x initially, and then is a function of the previous hidden layer. But it's a Gaussian process, and in fact a vector-valued Gaussian process. So there's many different ways you could do a vector value, but in this case we just assume each function is independent, or you could do whatever you like. So that's the idea of the deep Gaussian process. You might be asking yourself, oh, what happens if you take z to infinity as well, the inner dimensional layers? Well, then you actually get back to just a standard Gaussian process again. You don't get any effect. These bottlenecks turn out to be very, very important in a deep Gaussian process. So if I make these bottleneck layers larger and larger and larger and larger, all I'm building is what's sometimes called a deep kernel, putting that in a Gaussian process. Because what happens is that the distances between points as I take the width of z to infinities concentrate, and the expectations disappear. So actually, it's really interesting that I can take the width of these hidden layers to infinity, and that's good, that's very nice and complex. But if then I take the width of these additional latent layers, well, you still get a model, but it's just a Gaussian process. You can just flatten everything down again. So a deep Gaussian process where you don't have these intermediate bottleneck layers is just a Gaussian process. Okay, so mathematically, this is just a composite multivariate function. And as is a neural network. I think that we like to make a big fuss about these deep neural networks, but if you show this to a mathematician, they'll sometimes say things like, well, why do you bother writing that thing down on the right? Why don't you just write g of x? Which is fair enough. And the reason, of course, we do is because we can include all sorts of these beliefs about the way the world operates. If you're putting a convolutional neural network in one of your functions, or if you're going to use a recurrent neural network, you're encoding something about the way you believe the world operates. And the nice thing about these frameworks that we use is that the end result is the composition of simpler functions. So that's true in neural networks, and it's true also in Gaussian processes. But the interesting thing in a Gaussian process is that this is a composite multivariate function. So Gaussian process on its own, f of x, is a stochastic process. So this is a composite stochastic process. So it's not just saying something. So stochastic processes are amazing, they're very powerful, but they're frustrating in that there's only certain classes of stochastic process that are analytically tractable, like a Gaussian process or a Poisson process, Markov process, jump processes. So we should always be on the lookout for new ways of creating stochastic processes based on these component parts. And this is one, and it's the first time I've seen it done is with a deep GP, although people may have done it elsewhere. And the nice thing is it gives you a different class of stochastic process. The nasty thing is it becomes non-analytic. So another way of writing this down is through a Markov chain. So that's the sort of functional way, but in this case we're putting a prior over each function. So implicitly underlying each of these is a sort of probability distribution of what f1 is. That's a Gaussian process, that's a Gaussian process, that's a Gaussian process, so on and so forth. And then what you typically want to do is integrate over all the intermediate f's. and that turns out to be intractable. We have a lot of approximations for dealing with that. There's another tutorial in here later, so I'm not going to talk about him. But this is what we get, is this chain. It's just a chain. In fact, most deep neural networks are kind of chains. You could have skip connections, jump connections, that would change the nature of the chain, but it's a very simple probabilistic object. So I've put it that way up. I like to think of the latent variables often being in here, so I like my models that way up, and my observed variables out here. The neural network would often be the other way up. So why deep? I mean, if we look at the Gaussian process itself, it has some very elegant properties. So it has this interesting property in particular, that the derivatives of a Gaussian process are also a Gaussian process. That always fascinated me. Like, when I heard it from day one, I thought that was amazing. And then it took me a while to understand why it is. But the reason is quite simple. It's because the derivation of a function is a linear operator on the function. And any linear operator is equivalent to, in the discrete case, some sort of matrix operation. So derivation is simply a linear operation. So therefore, the derivatives of a function, of a Gaussian function, are jointly distributed as Gaussian for a Gaussian process. For particular functions, these covariance functions are universal approximators. So that's thought to be a big, exciting thing. I think it's a very uninteresting thing. The last time you had infinite data would be the last job you work on. But, you know, we never have infinite data, so we don't really care about the behavior of things in the infinite limit of data. What we care about is how rapidly they approach the sort of behavior we want. So I'm not so worried about that. But this Gaussian derivatives might ring alarm bells, and in fact it is quite a bad thing. So it can approximate anything, but it's got Gaussian derivatives, and there are lots of functions that don't have Gaussian derivatives. So any kind of jump function isn't Gaussian, right? So flat, 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 step, flat, 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 that is that's an infinite derivative at one point, and everywhere else it's zero. So any heavy-tailed function, and Radford has really nice examples of this in his thesis, processes that aren't Gaussian processes, with heavy-tail functions with big jumps, and is not a Gaussian process. It doesn't mean, by the way, you can't handle a jump with a Gaussian process. You can do, because you can parametrically encode the jump in the mean function, as Max was talking about earlier, or you can make two independent Gaussian processes either side of the jump. The problem is you have to encode it. So you're back to that old basis function problem before. So to go out of that class of models, the deep Gaussian process, from a process perspective, is this process composition. If I compose several processes together, I've got a new way of constructing complex processes based on simpler components. Now, this is something that I think, for me, this is totally obvious, but people don't really seem to spot it, so I just want to highlight it in one plot. We've got a process like this. We are absolutely not constrained to processes like this. I think it's very important to believe in models where you could take an observation off the side, right? Within this framework, this is just graphical models with Gaussian processes pumping between them, right? So every time I hear multitask learning or some kind of learning, this other type of learning, you can always write that down as a probabilistic assumption. I mean, it's a bit frustrating how many different names we have for types of learning, where we should just actually explicitly say what our assumption is about our data. So they're often conditional independence assumptions. And a really nice way of expressing conditional independence assumptions is with a simple graph. It's difficult if you've got many, many nodes, because it's very unclear what's going on. But if the links between the nodes are very, very powerful, then you can express those conditional independence assumptions in the graph. So here I'm just postulating that we have an observed variable that is perhaps closer to the input, and another variable that is further away. And I'll show you another example of my vision on that later. But the real challenge for these probabilistic processes is that you're propagating this probability. So at each of these stages, this is a probability distribution here. And integrating across those is equivalent to pushing a probability distribution through a nonlinear function, not just a nonlinear function, a nonlinear process. So if I imagine if I had a Gaussian distribution on this grid here, and then I map it through this nonlinear function here, then it's not going to look very Gaussian. In fact, it will typically be non-Gaussian and intractable. So a sort of thing people do, and David Mackay had really nice early work on this called density networks, which I think have been relooked at more recently, but were ignored for a long time, where you represent your distribution with a set of points, and you push those points through the nonlinear functions in order to represent your distribution on the other side. So that's like a Monte Carlo method. It's a simulation method. Quite a good way of dealing with it. So this has got cut off at the top here, but even in one dimension, if you put a Gaussian variable through a Gaussian process, what you end up with on the other side is a non-parametric one-dimensional probability distribution. So people get excited, oh, I've got a mixture of Gaussians. It can model 5 bumps if I've got 5 nodes. If I put a Gaussian through a Gaussian process, the thing on the right could have infinite modes. I mean, it's already a really powerful distribution. That's 1D to 1D. Having said that, it's not structured enough. I mean, there's lots of things wrong with it. It will often not be a good fit. So that's why you often want to go deeper. So I really got into the sort of thought of deep when it wasn't called deep. I think it was about 2001 when Jeff Hinton came to, as Max said, I was briefly at Microsoft Research and was talking about stacking Boltzmann machine models. And the point he made is that you could have abstract layers at the top and more detailed layers at the bottom. And that's something I'm always thinking about. So I'm trying to not just build regression models, but also build models where I'm integrating out the X at the top, like in a GAN, and then I've got those are the abstract features, and I drop down the model, I can get more and more detailed as I go through these nonlinearities. So, think of the universe that we're in. The latent process is that cosmic microwave background, and over time, we've pushed forward with a series of nonlinearities to produce us today. Approximately. Of course, if you do this with PCA, you don't get anything. PCA is really nice because, so stack PCA or stack regression. So I think of PCA because I assume I'm putting a Gaussian on top here. And at each layer, that Gaussian is going to sort of drop down into these different square. And you don't get anything nonlinear when you do that. And of course, we don't build neural networks with only linear activation functions for that reason. Actually, notice that the properties of this change, right? So it is true that the properties of this change, so you tend to get lower rank Gaussians as you drop down the network. So it's not that the same that you could put a univariate Gaussian here. This tends to be lower rank. This is lower rank still, lower rank still, lower rank still. And that always goes in that way. You can't unpick that. So if you do this with PCA, something does happen. It's just not very useful. So I'm doing the same thing here with the stack GP. So I'm just sort of taking the original GP. And look, this one's got quite folded over on itself. Look how complex it's got at the bottom. But these are motivating. I think that these motivated people doing some work on these processes to see what they look like, and I'm going to mention that in a minute. But this square now has had this corner folded over onto itself. Now, these are two-dimensional. Remember I said at the beginning, in the middle, that the width of these Z layers is very, very important in dictating the properties of the process. Well, here to visualize, it's just 2. So I'm mapping from the Gaussian process. I've got a random sample of a Gaussian process outwards, which happens to have folded this square over onto this corner of the square here. You can never unfold that because these 2 points will always map to the same place, right? So that's a property of this. And that happens in low dimensions. If I was doing this in infinite dimensions, it would never fold over onto itself. Everything's equally far apart in infinite dimensions. And actually these dimensions, the way we set it up, are independent. So that folding over would never happen. And that's why it stays a Gaussian process as we go to infinite dimensions, because this folding over doesn't happen. So as you reduce down to these lower numbers, you start to get these folding over effects occur. And that gives you these very non-Gaussian effects. Why have I lost the... look, if only it was Valentine's Day. And a bird. Look at that. Miraculous. And there's a man. See? Gee, I hadn't actually checked these. They're pretty good. Okay. So, now I think seeing those slides, David Duverneau was early interested in this, and with Ryan Adams and others, including Zubin Garamani, they looked at the sort of... He viewed this as a kind of pathology, which I disagree on. I think it's a property, and it's a parameter you should be controlling for, the dimensionality of these latent layers. You should be optimizing for it. But they did a very nice analysis, and what they showed is that the derivative distribution becomes more and more heavy-tailed as you go through the deeper network. So you tend to get the ability to model these jumps. Now, there's another really interesting paper that's just out on arXiv a week ago, prompted by me saying, can you put it on arXiv so I can talk about it? How deep are deep Gaussian processes? And this is an analysis by Dunlop, Girolami, Andrew Stewart, and others, which is very interesting because you've got these elegant processes right now. And if you think of the vanilla Gaussian process, it's just a Markov chain. So they look at how quickly that Markov chain mixes. And then you can answer questions like, well, If you want to understand the stationary distribution of how that Markov chain mixes as you go deeper, if it's ergodic, you can show that when it's ergodic, you can sort of say, well, actually, I don't need to have 100 depth of layers if the Markov chain is already mixing after 5. It's pointless because my prior probability is already telling everything you want. I think that's true, and it's a great observation. The only caveat I would have is typically you're optimizing hyperparameters of these models as well. And the assumption that they have is that those hyperparameters are static. The other aspect that I think both these papers don't really refer to is this important aspect that you very often want to structure the model. So you may have those side observations will really affect the conditional independent structures on this graph. So they're lovely theoretical analyses, but be careful by drawing too general conclusion. That's always true of theory, which is why we do practice. Oh, YouTube server's DNS address could not be found. So this was a nice video that David did that's associated with this paper. You can look it up, of showing the sort of ways in which these processes change the boundaries between places as you go deeper and deeper. It's a nice watch. Apologies, I can't show it. Okay, so that marathon data I used as a motivation example before. Remember, 1904, they got lost and were almost as slow as I am. So just from memory, this is the Gaussian process fit we had before. So the way I've chosen to fit this is I've just done a 2-layer Gaussian process. So one Gaussian process going into one dimension and then one dimension going out again. And the reason I've chosen that is so that we can visualize what it does inside. So I fitted that deep Gaussian process. Now, bear in mind, this is 20-odd data points. The size of this already is infinite parameters, right? But because they're being treated in a Bayesian way, we're not getting overfit. The actual parameters we fit in a maximum likelihood sense are 3 in this case. So the interesting question is what happens when we fit the deep GP? Well, this is the fit. So what you see now with the deep GP is it's done a much better job of understanding the sort of stochasticity in the process early on. What I like about this example, yes, you can do very, very complex mean functions with a deep Gaussian process. We already saw how complex it got after a few layers. But in this example, the main thing it's dealing with is the stochasticity in the process. So what you're seeing is that it's starting to tunnel down to understand that actually in the modern era, the variance around marathon times is low. Of course, as we move away from the modern era, as it predicts out into the future, it's starting to head back off. It will revert to something quite large. But on the left here, it's sort of seen this crazy result here, and it's giving very large variance here. So how's it doing that? Well, what we'll do is we're going to look. So pay attention to the bottom. This is year, and this is going from, I think the first is 1896. And the last one I've got recorded here, I think, is 2016. I didn't record 2020 yet. So this is the first layer. So this is the input to that hidden variable we've got inside. Look how simple it is. It's not doing anything super complex, right? But it's kind of informative what it is doing. That's actually the outlier point mapping into the hidden variable, right? So this isn't the output yet, but because it's an outlier, it's already an outlier in the hidden variable. It's broadly speaking saying it's linear for most of the time, but then crucially, it starts to curve off very subtly. And this flattens out. So all these are predicting to the same distribution of the hidden variable on this side. Right? So that since 1980 approximately, we're seeing everything is up here. Before 1980, they're moving from negative hidden variables up to positive hidden variables. This is the hidden variable to the output. Notice it's much more confident here, but there's uncertainty being injected into this. So this is conditioned on the input, right? So there's uncertainty being injected from the hidden into here. So look what happens. As we come in, the mean of these points, I'm not representing the uncertainty. The mean of all those points is clustering, right? So because the mean of those points is clustering, they also have a variance which moves them side to side in that way. But the function here is also pretty flat. So basically, they're all around the 3-minute per kilometer mark. Whereas these points here are changing linearly through time. So in this sort of section here, It's a linear function, broadly speaking, of a linear function. But it's ambiguous where it could put the uncertainty, but it's actually chosen to put the uncertainty on the first function. And why is that? Well, I don't know, but it's chosen to do it. And then on this bit here, although the uncertainty is sort of high, it's going between 2 and 1, the function is also flat in this region. So the end result is something that looks like that. So that's heteroscedasticity and effectively a change of length scale as well. Because what's happening, the effect of doing this, the effect of flattening here is equivalent to saying that the length scale has gone large. So it's actually allowing the process. So here the length scale is staying broadly the same, and here the length scale is going large. So that's why you're getting those flattening functions. Okay. So this data set is one that Brian Ferris collected for a collaboration with myself and Dieter Fox, where we were some years ago looking at inferring location given Wi-Fi access point strengths. The interesting thing about the data is I think Brian just walked around in a circle. I think he walked. I don't know how he got the data, but maybe looking at how many access points you can read and what level they're at. And it's got a really annoying noise structure because when the access point drops below a certain point, it just reads minus 0.5 in this case once it's been scaled. And then in these things here, right, it's all discrete levels as well. So you can see that it's not continuous. And this is real data. I mean, the amount of data that we look at in machine learning, real data has crap like this in it. By the time we get round to running our algorithms on it, it's often being cleaned up. So in order to deal with this, it's had to go for a very, this is a Gaussian process fit. So it's had to go for a very short length scale to sort of deal with the rapid change, which is artificial. Obviously, we should get rid of this. We should deal with this somehow. This isn't, a Gaussian likelihood isn't correct in this case. We should somehow reflect what's actually going on, but I've chosen not to here. Okay, this is the Deep Gaussian process. Now, it does have some interesting, slightly different artifacts, and I haven't investigated. So here, it doesn't go flat. It didn't work out that the length scale in this region is very, very long. Why? Because it's difficult for it to do that because other Wi-Fi access points are moving at that time, right? So it's only for this single output where it's dropped below. And I haven't given it the conditional independent structure for it to be able to work that out. With enough data, it might be able to learn that, and that's something we should experiment with. But this is relatively little data. It's 200 data points. But what we do notice is that look at the quality of the error bars have really improved. So it's sort of really, instead of diving down here and having a small error bar, it's not doing that anymore. I mean, it's a different fit. I'm not even sure I'd think it's necessarily better, but it's very different quality, and you can see you get this heteroscedasticity coming in as well. This wasn't known to the model, so this is what the model has in this case is an input regression is time, and it's regressing from time out to 30-odd access points simultaneously. Yeah. The Gaussian process has the advantage of doing this fit independently on its own, right? So that's why it gets this quite well. It's doing that on its own. So this is the path that Brian walked around. I think it was the Paul Allen building, I'm not sure, in UW. And this is actually, what we did here is we've got a one-dimensional input going to a two-dimensional latent space, going to a five-dimensional latent space, going to a 10-dimensional latent space. Right? So it's quite a deep model. And this is what happens if you look in the two-dimensional latent space. It's sort of reconstructed this, not perfectly, it's got a fold over on it, right? So that's wrong. But this is the loop that, ignore the fold, but if you go around like that, that's the loop he did. The fold's actually quite difficult to get rid of if you start with a two-dimensional latent space. I didn't have the patience to train it for long enough to deal with that. Okay, so next example is old example that Andreas did, I think in the first paper we had on this, which is illustrating one of the nice characteristics that it's very easy to build these type of structures where you've got some sort of time affecting some latent variable, and then you're going out from that to y1 and then out to y2. So this is a paper from like 2013 or earlier, 5 years ago or something. and then say, oh, well, this person also has something else going on. So what this data is it's two people walking towards each other and high-fiving each other. So because they're two separate people, I've created one output for each of those people, a shared latent space, which is about what they're doing together, and two separate latent spaces that are independent of that shared, and then the whole thing's governed by time. So actually, I think there are connections. I think I've got this wrong. I think there are connections from time to Z and time to Z2. We'll see on the next slide. And this is the sort of result you get in those latent spaces. So yeah, that's right. There was a one-dimensional going to two-dimensional going to three two-dimensional is what it learned. And in this case, it will just reconstruct as you go along here. It just reconstructs two people walking towards each other and high-fiving. But the interesting point is that it has these factorized space that it learns about the separate spaces. So you can sort of do these multitask learning things very easy. And it's very, very effective for multitask learning, actually. It's probably... We started building this type of model in an effort to get the structural learning right for the deep GP. But this type of model without the time on the top, this type of model on its own, it relates to inter-battery factor analysis work by one of the people that does. Is it Tucker? I think it was Tucker. Which is similar structure, but with linear models. So this is a nonlinear variant of this. And Sami Kasky does a lot of work on Bayesian linear versions of that as well, with Arto Klami and others. And this works very effectively even without the deep stuff in that case. So digits data sets. So another question is whether we actually really need such deep hierarchies, right, when we've got very low data. So I'm showing you quite low data. There's a reason for that. It's because these models are relatively slow to fit. There are a class of approximations that use stochastic variational inference where people have been doing billions of data points. But for illustration, today it's just easier to deal with these smaller examples where I have a better understanding of what's going on. So in the first paper, we sort of asked the question, do you really need a deep model when you've got only very little data? So for 150 data points from MNIST, so sixes, zeros, and ones, so in the first work, although I'm not sure, one of my other collaborators was saying he didn't find it easy to reconstruct this. But what we did is we tried, these W's are not the W's in the neural network. These W's are parameters we use to learn the dimensionality of those latent spaces, which we can do because it's a Bayesian setup. So what Andreas, who did this work, is showing here is that we started off with, I think, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17-dimensional initial latent space sitting on top of the USPS digit. And then we brought that down to 1, 2, 3, 4, 5, 6, 7, like 10 or something like that, then down to 8, 6, 4, or 5, or something like that, right? But the model itself learned to switch off two of these dimensions on the first layer. And the model also learns the depth. So it actually learns how deep it needs to go. So that's all done by marginal likelihood maximization, which we can do because we've integrated out all the parameters. And what you'll see, what Andreas did is he found a point in this high-dimensional space here, so represented by this 0, and he moved, it found a direction where when you moved, it opened and closed the top of that 0. Yeah? So these are continuous spaces. We're not looking at like the output of an individual activation unit. These are full functions. So they don't interpret the same way as when looking at a neural network. It's like looking at those additional hidden layers. So it's learned a localized feature that opens and closes in one position, the top of a 0, in that high-dimensional space. Here's another feature he found on this second layer, which opens and closes the base of the 6. You've got a 6 that is opened and closed there, so that's a bit of a broader feature. And then at this layer here, the second close to the top, he found a feature which moves between 0s and 6s, and at the top layer, there's a feature that goes between 1, 6, and 0. So the nice thing about that is that you're actually managing to fulfill this nice belief of that more abstract as you go higher up. Of course, when we did this, GANs didn't exist. They were a long way off, 5 years off. And this is all driven by probabilistic modeling. But bear in mind, it's 150 digits. I'm not super familiar on what everyone's doing in the low data regime, but one of my mantras is actually, in practice, when all's said and done, all data is low data. I'll come back to that in a moment. This is I've got some notebooks that I'm going to make available where I fitted a deep Gaussian process to some 1, 2, 3s, and 4s. These are just samples in a two-dimensional latent space. I just take a tour going around that two-dimensional latent space, which is sampled from a Gaussian process. So this is just work I did like yesterday or something to show that, to check my sanity that, well, actually, and Jen Wen actually mainly wrote the code, that these samples were working. So we're in this space, it moves. Notice, interestingly, how quickly it moves from 1 to 2. There's not a super large regime in between like you often get with these variational autoencoder models. Here's a region where it's gone somewhere where there's not much going on. But actually, this is just showing the mean function. These aren't samples. This is showing the mean function, okay? So there's actually a little variance around these samples as well, and the variance tends to increase when you go into these dodgy regions. So just to show you what the latent visualization looks like, there's the digits here. There's digit 1, nicely lined up. This is the top layer space, two-dimensional, and that's going down to a five-dimensional space, and there's some views on the five-dimensional space which it projects to, right? So all those blues here are effectively a nonlinear Gaussian mapping from this section of blues here. So they have broadly the same structure with some sort of subcluster. That's probably the ones that go in the opposite direction. But they're distributed across the five-dimensional space. Now I want to leave some time for questions, so I'm going to rush through the bit I have on uncertainty quantification, which I think is really important. Well, I'll pause at some moments, and I'll show you a notebook you can use to play with. But this has always been my vision, like for a number of years now. This is the sort of thing we should be trying to do. So it's titled Deep Health, and what it's trying to show is, look, if we really want to do the whole health of the whole individual, we need something much more complex and rich than these simple probabilistic graphical models that only interact at certain levels. And we need to be able to, these things say environment, epigenomics, genomics, gene expression, social network, biopsy, X-ray treatment, clinical measurement, survival analysis. And within this framework, you can envisage pulling all this together like a jigsaw, because it's like these very flexible, low-dimensional latent variable models that can be stuck together. And just to sort of illustrate that, other people are thinking about this type of thing, this year's NIPS, there's Gaussian process, nonlinear latent structure discovery in multivariate spike train data. That's Wu et al. That's a paper this year. That paper is a one-layer GPLVM with Poisson noise on the output. Doubly stochastic variational inference for deep Gaussian processes by Selim Bailey and Dijzenroth. That's a paper that allows you to do stochastic variational inference for regression, deep Gaussian processes, and I think they've done up to 1 billion data points. I'm very, very excited about this. I haven't read it in detail, but this is exactly the sort of thing I want to see. Deep multitask Gaussian processes for survival analysis with competing risks, Allah and van der Schaar. And this last paper is, it's a talk. I'm not sure if the others are, some of them are spotlights, the others at least, maybe even talks. Counterfactual Gaussian process for reliable decision-making and what-if reasoning, Shalom and Saria. That one I particularly like because it's actually about single Gaussian processes, but it's about understanding how to deal with treatments in the clinical environment and causal modeling in that domain. But it shows how a rich probabilistic model can be used with a nice framework like counterfactual reasoning to really make practical judgments in the real world. And my kind of hope is that these deeper Gaussian process models, they will hopefully, if we can fit them at the scale we want, they can pull that complexity of model together and do things like causal reasoning. And the other thing, we've got an archive paper where we put differential privacy on a Gaussian process. And of course, that's with all this in mind. Basically, anything people can do on a Gaussian process, you can then put into these frameworks. And differential privacy is something very important if health is important. So other works that I kind of find interesting are deep survival analysis, Ranganath et al., which also is, I think, thinking along similar lines, but that's not at this year's NIPS, but an old one. Something that I haven't talked about at all today is that we can do all this for recurrent neural network type structures. All the same tricks apply, and we had a paper at ICLR, good heavens, 2 years ago, apparently, where we were showing how that's done. And that's closely related to what people would call Gaussian state space models. And there's work on Gaussian state space models at this year's conference. And then I want to shout out to my student, Alan Saul, whose thesis on Gaussian processed approaches, based approaches for survival analysis is also looking a lot of these challenges around how you do survival analysis in this context. With survival analysis, it's very difficult because the information is very sparse. Okay, so that's 3 minutes before the questions, right? Okay, cool. So I just want to whisk through in the last 3 minutes before the questions. Why I care about this. So multi-fidelity modeling. I mean, deep nets, so they're a very powerful approach to images, speech, and language. Believe it or not, that's not the only challenges we have. My own approach is that you can also look at these with deep Gaussian processes. That's fine. I would suggest that, I always think if I ever were to play, I don't know, for Real Madrid, I wouldn't say I played the same position as Ronaldo. I would say I played goalkeeper or something. Don't try and compete with other models where they're already clearly strong. And those models are very strong in these very large data where you don't need the uncertainty so much. So you can certainly augment them with Gaussian processes, and we've done that, others have done that. But actually you should look at other things. So I think that one of the most interesting areas is uncertainty quantification. And I don't look at my spelling, it's all terrible. And it's related to other areas like probabilistic numerics, surrogate modeling, emulation. All these areas are similar, and they're very much about the way the real world interfaces with the simulated world, and choices you make, decisions you make about should you fire another simulation off, should you acquire data in the real world, should you take an action. All these things need to be driven by uncertainty, and the general area of uncertainty quantification, UQ, basically stipulates that. For me, I'm not a fan of AI as a term. In fact, I really dislike it. I'm constantly now being asked to talk about why things I do are like humans when they're clearly not. But there's loads of fields where people have been thinking about these challenges, in particularly UQ. If you read like what it says about UQ, uncertainty quantification is the science of quantitative characterization and reduction of uncertainties in both computation and real-world applications. It tries to determine how likely certain outcomes are if some aspects of the system are not exactly known. Of course, you could say, we're trying to be brains, and you might get more people coming to your conferences. But these guys, it's filled with applied mathematicians and statisticians and very other things. And for me, like at Amazon, this is a vital tool when you're interacting between the physical and the virtual world. Amazon, to me, is the only place where you can imagine any advance in AI and it will immediately affect the bottom line of the company. There's applications for anything you invent, like today, like now, because it has this massive physical infrastructure and a massive virtual infrastructure. And so for me, uncertainty quantification is very important in that space. Another example from former life consulting, designing like an F1 car, you need to do computational fluid dynamics, you need to do wind tunnel, you need to do track testing. How do you combine them to make a decision about whether the modification you've made to your car is making the thing go faster? How do you choose to do which to do next, particularly when you're under limited budget as they are? So they're restricted how much CFD they do, they're restricted how much wind tunnel they do, and they're very restricted on how much track testing they do. So these are the sort of questions that, I don't know what AI is, but decision-making under the presence of uncertainty when you've got constraints seems to me to be something that we should be looking at, and broadly speaking, that's covered by the domain of uncertainty quantification. So we've done a little bit of work on that with collaborators at Brown and MIT. I think that's a really exciting area, and the way we do it is we combine these different facets of data together, different fidelities and multi-fidelity optimization through deep Gaussian processes. There's a notebook online that I don't really have time to show you, and I'm getting a 0 from down in the benches. So I'm going to stop there and take questions, but just to sort of say, I was very lucky that a number of people, including my wider research group, particularly these people, have put a lot of help into feedback on the presentation and preparing data sets. And the main conclusion is, what's stopping these things going forward? Well, if you compare to neural networks, we just don't have the quality and size of code bases that allow us to fulfill the promise. And basically, it requires a lot of algorithmic understanding to deploy these. And it shouldn't be like that. If the promise is that I can just compose models in these various ways, we need to have the power and flexibility of the neural network frameworks so that people can do that in the comfort of their own homes without sort of calling you up and saying, can you fix my algorithm? So our focus has been Gaussian processes being driven by MXNet, the neural network training framework, and we're putting a lot of effort into scaling things up and making them work well for composition of GPs with neural networks and other methods. And that's it.
All right, so don't everybody walk away. We have some time for questions. So please go to the microphones right there and there. So I have 6 questions, and I cannot believe that 7,000 other people cannot come up with one question. There's a question there. Thank you very much.
The question is, where's lunch?
Thank you so much for an interesting talk. One bottleneck that you mentioned in applying GPs to large data sets is representing the kernel matrix. The suggestion that you showed in the talk that worked very well was like attractor points and low-rank approximations. The work that I'm presenting at NIPS with Yi Ding and Rishi Kandor proposes multi-resolution approximation to large matrices like this. It seems to be a tension in growing data sets of whether you should make a low-rank assumption or some more complicated assumption about the structure of the data. I wonder what your thoughts are in applications you've seen and where you see that heading.
So, yeah, there are other approaches. And my main thought is the biggest problem we face is that we all make these approximation methods, try them on our 5 data sets, and they don't get tested in the real world. So if we could just get them out in software so that people could really find what works in practice, because we're so busy doing new methods, we often aren't deploying them, and we need to bridge that gap. But as many approximation methods as possible is great. Yeah.
Thank you so much for the nice talk. So there's something I couldn't understand. It's about learning, and coming from like the neural network community, where I need to have an online adaptive setting. I was thinking whether this framework could do something about control theory applications, such as like tracking. Do you have a learning rule? How would you? Does this deep GP Gaussian process?
Is there a learning rule?
Yeah.
Yeah, so you can compute gradients, and the learning rules vary depending on what approach you use. One of the most promising is this thing called stochastic variational inference, where you combine variational approximations with stochastic gradient descent. It's an idea from David Bly and Matt Hoffman and others. And that seems to work very well for Gaussian processes for big data. But there's still, again, we just need better software and to deploy it in more places. It's not easy to implement. That's one problem.
So if I have new samples, an online setting, can the deep Gaussian process get
so
adapted?
if you were online, yeah, so that's another really nice paper. Rich Turner has a paper with Tang Bui again on continual learning with Gaussian processes. In the online setting where you actually want to modify your model, I think that's a very, very interesting work to take a look at. But yeah, it depends whether you mean like I've got a static model that I'm training with a stochastic gradient, or I'm actually deployed the model online.
Thank you so much. Thanks.
How many do you want to take?
I don't know.
Hi, nice talk. Thanks. So I have a question about the uncertainty quantification. I agree with you a lot about we need to deal with uncertainty quantification, because when we want to apply machine learning to real problems, we need to know what's the confidence interval, what's the uncertainty there. But for applied mathematicians, they already developed a lot of toolkits for uncertainty quantification, like the generalized polynomial chaos, the Monte Carlo-based method. What kind of advantages do you think that the machine learning people can bring to this field?
I don't personally like to think of, as I've grown older, machine learning people and statistics people and Other people, I just like to think of problems and solving them. Polynomial chaos expansion, I don't know much about, but the other main technique people use is Gaussian processes, and there's clearly situations where they're limited in approximating, and we've already done stuff. In fact, there was a notebook I didn't have time to show, where you use deep Gaussian processes as your surrogate model. So I like working with those guys. I mean, they've got a lot to bring. They think very deeply about their problems.
Yeah, those methods are kind of suffered or not from curse of dimensionality.
Yeah, there's quite a big queue behind you.
So there's a long queue behind you, and in fact, we're already running over time. So I'm going to have one more question, and then the rest of the people, maybe they can come up afterwards and come here to talk with Neil.
Hi, Neil. Thank you for the talk, and it's a great job recovering from the technical difficulties during the talk. I have a question about uncertainty. So you have... there's a variety of ways people are trying to come up with uncertainties out of neural networks, and Yaring-Gels thesis and what you described and a few others. Which ones are better when, in your opinion, and what's what are the advantages?
So I think the question was, because I have trouble hearing with the echo, but was it about the uncertainty methods in neural networks?
Yeah, basically, in your opinion, what are the advantages or disadvantages of other methods or versus this?
I have to say I'm really skeptical about them. I mean, it's very hard to do good Bayesian inference when the parameters are highly correlated. I did it in my PhD thesis. Hybrid Monte Carlo works really well, but to get the quality of uncertainty estimates, you really want the non-parametrics, number one. That's really important, so the error bars go up where you haven't seen data. I mean, you see plots and you sometimes wonder, okay, is that the real plot you got? Because when I've had people working on it, the error bars don't look very good. They tend to look, the problem tends to be that if you don't get the correlation structure right, all those error bars of everything moving at the outside is to do with weights moving together and basis functions flopping around. So those tend to be difficult to find. I mean, Max has some of the best techniques for doing this at scale. So maybe he knows better than me, but...
Well, I think we should really stop here and thank Neil again for a wonderful tutorial.